out as a regular line pilot in the Airbus A320. It literally was right out of training.
And the benefit of that was that he knew exactly the checklist to turn to, and that's exactly what he did.
The fuel remaining, engine mode selector, ignition.
Crews are highly trained in emergency procedures, and the main thing is to follow procedures in this instance, and that's exactly what First Officer Skiles did by grabbing the quick reference handbook and turning to the appropriate checklist.
But as investigators examine the checklist for restarting this plane's engines, they make a troubling discovery.
It was assembled for an event that occurred 20,000 feet in the air, where a crew would have plenty of time to slowly and carefully go through a 3-page checklist, the end of which was, how do we ditch the airplane?
So it was a 3-page checklist, and really I only got to about the page and a half through this checklist in the time that we had.
Airspeed optimum relay.
The crew spent a lot of time trying to restart the engines when they could have been focusing on preparing the airplane for the ditching.
300 knots. We don't have that.
We don't.
Overly complicated checklists have played a role in deadly plane crashes in the past. In 1998, a fire broke out on board a Swissair passenger jet. The checklist the crew used for that situation would have taken them up to half an hour to complete. It's a half hour they didn't have. But on Flight 1549, the checklist was far from the greatest challenge facing Sullenberger and Skiles.
I'm not sure we can make any runway.
Water landings are notoriously difficult because unless they're perfect, they can be catastrophic. In 1996, after a hijacking, an Ethiopian Airlines captain tried to land off the Comoros Islands when his plane ran out of fuel. His left wing hit the water first, causing the plane to cartwheel. It was ripped to pieces. Of the 175 people on board, only 50 survived. Investigators soon learn that none of the major airlines use simulators to teach pilots how to land on water.
Training for ditching in a simulator is very difficult. We don't have the models to accurately simulate what an airplane would do when it touches down on water. Given the rarity of this type of event, it would be very difficult to justify training pilots for this type of event.
But even without ever going through a simulation, Captain Sullenberger got almost everything right. He kept the nose up and wings level. He let the tail hit the water first, slowing the jet down enough so that it survived the impact.
Nice flying.
NTSB investigators turned to their own simulation to answer a vital question.
This is the captain.
Did Sullenberger have to land in the Hudson?
Brace for impact.
Or could he have made it to a runway?
Mayday, mayday, mayday. This is Cactus 1549. Hit Earth.
Investigators studied Chesley Sullenberger and Jeffrey Skiles' actions in the moments after their plane collided with birds.
Ignition.
We wanted to know, did the pilots do the right thing? So what we did in the simulator was we tested exactly that. Was there enough energy to make it back to LaGuardia? And what we found was that about 50% of the time we were able to make it back to the airport.
But when a 35-second delay is imposed after the bird strike to account for the crew's attempt to restart the engines, all of the simulator pilots crash before reaching the runway.
When we took into consideration the decision-making process that Captain Sullenberger went through, we realized that it was not possible to make it back to the airport.
Cactus 1549, runway 4 is available.
There's no doubt.
We're going to be in the Hudson.
Putting the plane in the Hudson was the right call. Sullenberger didn't have enough altitude to glide to either LaGuardia or Teterboro airports.
Got one roll. Both of them rolling back.
The investigators also discover that Sullenberger made a decision that wasn't at the top of the checklist, one that was critical to the survival of everyone on board.
I'm starting the APU.
On commercial jetliners, the engines provide power to electrical systems. If the engines stop working, the crew eventually loses those systems. The APU is an emergency generator that keeps some things running.
The APU allowed him to still see his screens, the instruments still worked.
It also allowed the A320 itself to assist with the heroic landing. The APU provided power to the plane's electronic brain, stopping the pilots from making any potentially dangerous moves. It kept them inside a so-called flight envelope.
By starting the APU early in the sequence, the flight crew was able to maintain the flight envelope protections, which prevented the airplane from stalling when the airspeed got too slow.
It's right on the edge of stall speed.
The flight data shows that Sullenberger was going slower than the ideal speed.
The airspeed during the accident sequence got about 20 knots slower than it should have been for this flight.
But the A320's flight computer is designed to constantly adjust the plane's pitch and keep it from stalling.
We definitely could have had a much more catastrophic outcome had the airplane actually stalled.